All right, we're going to start our next topic with a couple of examples before we get into the details of the topic. So here's our situation. We've got a theater selling regular and discount tickets. Friday night, they sell 25 discount and 45 regular tickets, and they take $650 from this. And Saturday, 23 regular and 23 discount and 51 regulars are sold, and they take in $694. We want to use this information to see if we can figure out the ticket price. So the idea is, as in most problems, we need to understand and name things. So, right, I want to encode all this information into math. And so the first thing I'm going to do is give names to the two things we're looking for, right? We obviously want those things. We know at the end of this problem, I should have something like D equals a number. If D is going to be my discount price, and we'll use R as our regular price. Right? So what do we know about these two numbers, or about these two variables? Well, I know that on Friday, the money I got from the discount tickets, which would be 25 sold times the price, this is going to be in dollars, plus 45 regular tickets sold times the price of regular tickets, and $650 was earned. I'm going to not write the units to keep things simple. We just know that this entire equation's units are in dollars. And then a similar thing, excuse me, on Saturday, we've got 23 discount plus 51 regular is equal to $694. So there's a couple methods. I'm just going to go ahead and show you one. And the idea, what I'm going to do is, right, we can't solve an equation with two variables, right? For instance, let's just do a really simple version of this. If I have A plus B equals 2, right, I can't solve to get A equals something. I could come up with several solutions here, right? I know that for instance, A could be 1 and B could be 1, or A could be 2 and B could be 0, or A could be 3 and B could be -1, or A could be 2.5 and B could be -1/2, right? There's an infinite number of solutions there that we can't lock it in. But what happens when we have two equations like this, sometimes they both have infinite solutions independently, but there might only be one or several that solve both of them. And so one of the way I think about it is I kind of want to take the information from one and import it to the other. And one way to do this is to take this equation, I'll take this first equation, and realize that I can rewrite this as a relationship between, more directly between D and R. So for example, I could subtract 45R from both sides, and then multiply both sides by 1/25. And that tells me that in order for this equation to be satisfied, whatever R is, D has to be, whatever value of R you find, this is how you would find the value of D, right? If you know R, you'd have D by this equation, right? Now we're going to take that information and put it into this other equation. In other words, I'm going to rewrite the equation down here. I've got 23D plus 51R is equal to 694, right? But instead of writing D, I can replace D with this expression, 1/25 times 650 minus 45R. Right? And now I'm staring at an equation with only one variable, right? In other words, another way to think about it is it seems like we have two variables, but they're not free of each other. You know, if I pick a value for one, the other one is determined. So really, only one of them can vary. Just like when I have A plus B equals 2, if I choose a value for B, at that point, A is not a variable anymore. It's a constant. So let's work out this equation. So I could multiply the 23 through, get 23/25 times 650 minus 45. Every time I write that 5, I go too far. Plus 51r is equal to 694. If we multiply this through, we end up getting 598 minus, I did a little bit of this work ahead of time, 207 over 5r plus 51r equals 694. I can subtract the 598 from both sides and at the same time combine the r terms. And what you end up with is 48 over 5 r is equal to 96. And then I multiply both sides by 5 over 48. And that works out to be 10. Okay, so we have a value now for r, but I can take that value and immediately get d. I now know that d is equal to, so I'm looking up at this, 1/25 of 650 minus 45 times 10. Well, that's 650 minus 450, so it's 1 over 25 times 200, or d is equal to 8. So our discount price is $8 and our regular price is $10. Okay. Let's take a look at what this means graphically. Right, so let's see. Right, these two equations, 25d plus 45r equals 650. Or let's look at, let's actually look at this one for a second. Whoops, sorry. Let me pull that back on screen. There we go. So looking at this equation, right, I could rewrite this as, let me just check which one I made, x and y. There we go, 25, 23 was, okay. So I'm treating my d as the x coordinate. So if I take this equation right here, I can rewrite this as 51r, or actually I did all this work already, sorry. This equation right here, d equals 1 over 25 times 650 minus 45r, you might recognize that as a linear equation, right? We can actually tell in this initial step, we've got two variables, neither of them is raised to a power, they're both linear terms, right? They're just like x and y are linear terms. They're not square, they don't have radicals or something else happening to them. So that means their graphs are lines. So for example, this first, there's the graph of the first line. These are all solutions to different prices for discounts and regular tickets, where if you had 25 discounts and 45 regulars, you'd end up with $650, right? Now, if we add in the condition from the second night, 23 discount tickets and 51 regulars, that's this other line. Let's make this a little clearer. Right? That also has an infinite number of solutions, right? There's all these different solutions to that equation, but there's only one that we found, 8, 10, right? We had 8 for our discount and 10 for our regular. That's the only one that satisfies both of them, right? So that's graphically what we just did algebraically here, okay? All right, let's do another example. All right, so now we have a boat traveling a route 210 miles on a river, okay? When it goes downstream, when it's going with the current, it takes the boat 10 hours. When it goes upstream, it takes the boat 70 hours. Okay, it's fighting the current now. What we want to find is what is the boat speed and what is the current speed, the current in the river, right? We're going to assume both of these are constant, right? This is really an approximation, but it's fine. This is just to see the method. So assume the boat goes at its engine is putting out is pushing it at a constant speed, and the river is moving at a constant speed. So let's do a similar thing we did last time. Since we're looking for the boat speed and the current speed, I'll take B to be the boat speed, and I'll take C to be the current speed. So how do we go about this? Well, we know that when going downstream, right, going with the river, the actual speed the boat's going. So let me make sure I'm clear about this. When I say boat speed, I'm saying this is the speed it would be going in still water with the engine working like it's working, right? It's the speed it's putting out. However, it's moving with the current, so it's going to be going a little bit faster, right? So in other words, if you take that boat speed and add the current to it, you get the speed the boat's actually moving relative to the land in this situation when it's going downstream, right? Well, we also know that trip of 210 miles took 10 hours. So that means that if we take 210 miles divided by 10 hours, we're getting 21 miles per hour, right? So in other words, I know that B plus C is equal to 21, right? I'm going to assume that this is all in miles per hour. Okay. On the other hand, when we move in the other direction, the actual speed the boat goes relative to land is how fast it's trying to go minus the fight it has to do against the current, right? And in this direction, we get 210 miles over 70 hours, which means B minus C is equal to 3 miles per hour, right? So it goes significantly slower in that other direction. Okay, so we could do something similar to what we did last time, but let's try something a little different here. I've got B plus C and B minus C equal to these numbers. We can combine these equations. In other words, I'm going to take B plus C equals 21, and I'm going to add B minus C equals 3. I'm going to add these two equations. B plus B is 2B. C minus C is 0. 21 plus 3 is 24, which gives me that B is equal to 12. Right? So we have this notion that there's like information, both of them, we're putting that information together. Here it was convenient that those C's canceled out. That was the crux of this. We'll see later that if we don't have that perfect canceling, we can still do things, which we'll see later, but you can multiply equations to make those things match up the way you want. But we'll get to that in a bit. So B is equal to 12. If I want to find C, I can choose either equation, right? For instance, B plus C is equal to 21. So that means 12 plus C is equal to 21. So C must be equal to 9. Okay, let's take a look at that situation. Right? Again, those two equations can be thought of as lines, right? The red line represents the equation we get from going downstream, going with the current, x plus y equals 21. And upstream is the blue graph here, and it intersects at 12, 9, right? Where our boat speed is 12 and our current is 9. Okay? So what we've just looked at, in both situations, the way we solved these problems was by using a system of linear equations. In particular, this was a 2x2 system, meaning it had two variables and two equations. Okay. Now, in general, a system of linear equations can be two or more linear equations made up of two or more variables, right? So linear equation just means nothing is squared, nothing is cubed, nothing's got square roots or cube roots, just variables times coefficients added together and constants, right, in our equation. So something like 5x minus 3y plus 2z plus k equals 14, and 2x plus y equals 3. This would be a system of linear equations. This is an ugly one with different numbers. It's not something we're going to be dealing with, but just anything of this form, right? For a 2x2 system, we're specifically looking at two variables and two equations, right? And that's what we had in both of these examples. We had b and c were our variables, and we had these two equations. Up here we had d and r as our variables, and we had these two equations, okay? When we solve systems, we're trying to find values of those variables, right? Like we saw in this case, we can picture them as coordinate points that make both equations true, right? So you find a single x value, a single y value, if those are your variables, that makes both equations true. When we do this, there are different possibilities, right? We might have what we call a consistent system, which has at least one solution. Oops, forgot an L in there. We have an independent system where we have exactly one solution, and an inconsistent system no solutions. So let's take a look at examples of each of these, right? So in the two cases we just did were independent systems. They're consistent and independent systems because they both had one solution. So let's look at a couple of the other. Well, let's just look at one more of these. So let's say I have this equation: 2x plus 3y equals 7. Let's say I have 4, and then 4x minus y is equal to 5, right? Let's solve this in two different ways. Let's solve it the way what we'll call the substitution method. That was the first way we solved equations just a moment ago in the ticket price problem. So I'm going to solve this for either one of my variables. I'm going to take this equation, 4x minus y equals 5. I can rewrite it as 4x minus 5 equals y. And then in this other equation, I can then write 2x plus 3, 4x minus 5 is equal to 7, right? I'm just substituting that value for y, or that expression for y, into the variable y in the first equation. And now I just do some algebra. So 3x plus 12x minus 15 equals 7. We get 14x equals 22. So x equals 22 over 14, or 11 over 7. And that would make y is going to be 4 times x, so 44 over 7 minus 5. Let's make that 35 over 7 so that we can subtract here, and so we get 9 over 7, right? So it has a single solution, right? This is the substitution method. Let's try this now using what we'll call the elimination method. So what I'm going to do here, remember in that in the both problem, we had a plus c and a minus c in our equation, so we added getting rid of one of them. I don't have that here, but what I could do is take equation 1. Let's take equation 1 and multiply it by -2. So -2 times 2x plus 3y equals 7 gives me -4x minus 6y equals -14. And I'm going to add that to the other equation. Right? Well, notice what I did. I multiplied it by -2, so I'd have a -4x and a positive 4x. I get -6y. Minus 6y minus y gives me -7y equals -9. So y is equal to 9 over 7. Notice we got the exact same answer, right? And then we could come back. We could use either equation. Maybe I plug 9/7 into that second equation. Equals 5. So 4x equals, so this is 35 over 7 plus 9 over 7, which is 44 over 7, and then divide both sides by 4, and I get 11/7 again. So as we expect, gives us the same answer. Let's look at this graphically. There's my two equations, 2x plus 3y equals 7. There's the two lines, and there are the points 11/7 and 9/7, right? At that intersection point, right? So either of those equations on their own have infinite solutions, infinite points that make the equation true. That's what the graph of their lines are. But there's only one point that makes them both true, right? The intersection of those two lines. All right, we got two more to do. Let's look at this system. X minus 2y equals 3. 2x minus 4y equals 10. Okay, let's use that same method again. We call that the elimination method. There's another, the addition method, I've heard it called too. I like the elimination method. So I'm going to multiply. Let's just do the same thing we did last time. I can multiply the first equation by -2 to get -2x plus 4y equals -6. And the second equation is 2x minus 4y equals 10. Let's see what happens. So -2x plus 2x gives me 0. 4y minus 4y gives me 0. So I have 0 on the left, and I have +4 on the right. It turns out 0 does not equal 4, so something has gone wrong. However, there's nothing wrong with what we did. What has gone wrong is this. We had these two equations. We wanted to figure out where both of them were true. Here's our picture. There's our first graph, x minus 2y equals 3. And here's the second one, this red, whoops, that's too much of a zoom. This red line, that there is no intersection point, right? There's no point that makes both of them true, which is what we found before. They are, in fact, parallel lines. And so we went looking for a solution. There wasn't a solution. And since that's why we get this nonsense back, right? 0 equals 4, which it doesn't. And so we know that something, these two, in this case, our system is inconsistent. There are no solutions. All right, let's do one last example. 3x plus 6y equals 9. X plus 2y equals 3. All right, in this case, let's use the substitution method. This second equation is really easy to rewrite as x equals 3 minus 2y. We'll put that into the first equation, so 3 times x plus 6y equals 9, but I'll write x as 3 minus 2y. So I get 9 minus 6y plus 6y equals 9. The 6y's cancel, we get 9 equals 9. So we can't solve for a variable here, it just disappeared on us. But what we got back was something that's true. Well, what's going on here, what this is telling us is, let's look at this system. Look at these two graphs. Here's our first line. Here's our second line. If you missed that, the second graph went right on top of the first, right? So here's the second graph. Here's the first graph. They're actually the same line, right? Any point that solves the first equation will also solve the second equation, right? And so this is an example of a consistent system where it has infinite solutions. Every single, any point that satisfies one of the equations satisfies the other one, right? And so that's why we didn't get back nonsense this time because we went looking for a solution and they are solutions, but this is a way of telling us that, we didn't get y equals 3 because y can be anything, right? 9 is always 9 no matter what y is because for every y value, there's a solution. Now, depending on that y value, the x will then become determined, but there is still an infinite number of solutions. Okay, and that's it. This is the situation when we're talking about 2x2 systems of linear equations. We can picture them both as lines, and we can use our substitution method or our elimination method to go looking for solutions. When we find a single solution, we're talking about the intersection, a single intersection between two lines. If we can't find solutions, we're looking at parallel lines. Or if we find infinite solutions, we're looking at two lines that are actually the same line. Okay, that will be it for this one. Thanks, everybody. I will see you next time.